So we're finally getting to the point in this unit where we actually could start doing a little bit of calculus. And so this is really pretty cut and dry. It's we're talking about vector valued functions, but really, we're talking about parametrics. I mean, that's what this whole thing has been really kind of about, is setting up parametrics. And we've talked about parametrics a lot in this class, so these are no different. All we're going to do is, if we want to find the derivative, we're just going to take the derivative of each individual component, or each individual parametric expression, and that goes for three dimensions as well. So either way, we're just really taking a straight derivative here. So taking a look at this vector valued function r of t, I want to find the derivative r prime of t. So let's go ahead and take the derivative of the x component. So taking the derivative of 4t to the 1/2 is bring down the half. We get multiplied by the 4. We get a 2t to the minus 1/2. And then that's the I component, so we stick with the I directional indicator. And then we're going to take the derivative of t squared times the square root of t. So if we think about this, this is t squared times t to the half. And so that's t to the, think about it, squared and half, that's t to the 5/2 in the j direction. So taking the derivative of that, we bring down the 5/2, t, and then we subtract 1, which is 2/2. So t to the 3/2 is the next component. And then taking the derivative of the natural log of t squared, and that's the k direction. So we're talking about this is kind of a u sub. We can think of this as the u is equal to t squared, so the natural log of u times du dt, chain rule. So we're talking about 1 over u times du dt, so du dt is 2t. So we're talking about then plus the not the natural log, plus 1 over u, so 1 over t squared, 1 over t squared times 2t in the k direction. So there's the derivative. We'll tidy that up and make it look a little nicer. That's 2 over the square root of ti plus, I don't think that can be tidied up at all, 5/2 t to the 3/2 j. Oh, I just noticed I forgot my j component right there. And then this can be tidied up a little bit. This would be 2 over tk. So there's the derivative of the vector valued function r of t. In terms of properties of the derivative, we're talking about all those typical properties. We've got our constant rule. We've got our sum of the derivative or derivative of the sum is a sum of the derivatives. We've got our product rule, written two different ways, really. This is actually really a dot product, but it ends up being mathematically the same. We have our composite function rule, and then this is actually more dot product information. These are real obscure, so we could actually kind of I know I've got a red line through this one, which is called the cross product, which we don't cover in this course anyway, but we could actually probably draw green lines through these. Very, very low probability. In fact, composites, probably not so much in parametrics. So all of those things are as they've always have been in calculus, just in terms of the properties of a derivative. If we talk a little bit about integration, really all we're doing is we're integrating as we've always integrated. So if we want to integrate a vector value function, we're just going to go ahead and integrate each component. For definite integrals, we can go ahead and evaluate and get a numeric answer. For indefinite integrals, then of course we're looking at adding a constant of integration here. Likewise for 3 dimensions, so this is 3D and this is 2D. And so we'll talk about that constant of integration as we kind of progress here through these examples. So here, let's evaluate the indefinite integral. I'm not sure evaluate is the right term. I would probably say anti-differentiate, because I don't see any upper and lower limits. So I don't really agree with the word evaluate. But either way, we're just going to end up integrating this. So we're going to integrate each component. So we have to integrate 4t cubed. And so we're going to go ahead and bump up the power to a 4, divide by that. 4 divided by 4 is 1. So our I component is going to be t to the 4th. And then, of course, after we integrate, we get a constant of integration. So I'll call that C1. That'll be the constant for the x component. So that's in the I direction. So we can just write it kind of like that. Integrating 6t, bumping up the power to a 2, and dividing by that 2. 6 divided by 2 is 3, so this is 3t squared. And I'll give that its own constant. So there's our constant in the y direction, or the j component. And then this is of course minus 4t to the half. So bumping this up is 3 halves. And dividing by 3 halves, this might take a little more thinking. Minus 4 divided by 3 halves is the same as saying minus 4 times 2/3. So we get a minus 8/3. So this is going to be minus 8/3 t to the 3 halves. And I'll give this a C3, constant of integration of its own. And so there is the integral of that vector valued function. We won't evaluate the constant of integrations until we get some initial conditions. For this one, we have a definite integral, so we'll integrate these and then we'll plug in the upper and lower bounds to come up with a numeric answer. So when we get to this level of difficulty, I kind of like to break it into its x and y and z components, and just go ahead and work through the mechanics of doing the calculus and then put it together at the end. So we're going to integrate t dt from -1 to 1. That's what we need to do. So integrating that's half t squared. We're going to evaluate that from -1 to 1. So that's half times 1 squared minus a half times -1 quantity squared. Figuring all that out, that's 0. Okay, looking at t cubed. So we're going to integrate t cubed dt. That's 1/4 t to the 4th, and that's from -1 to 1. Evaluating that from -1 to 1, so we got 1/4 1 to the 4th minus 1/4 -1 to the 4th. Interesting. That ends up being 0 as well. The last component, -1 to 1, cubed root of t. So cubed root of t is t to the 1/3 dt. And so integrating this, bump this up by 1, that's 4/3, and flip it, so it's 3/4 t to the 4/3 from -1 to 1. Interesting. So this is 3/4 1 to the 4/3 minus 3/4 -1 to the 4/3. Also ends up being 0. Interesting. It just ends up being what it is. So when we integrate this vector valued function, so this vector valued function would be drawn in 3 dimensions, and if we take that integral and find the area under the curve, we have as much above the curve as we do below the curve. We must have some symmetry about the origin here. And so it looks like we have 0 I in the I direction, plus 0 in the j direction, and we could say minus 0 in the k direction, or we could just call it 0. Yeah, either way. As we look at the next one, now we have some initial conditions here. We have an initial condition for the derivative, and we have an initial condition for the function itself. So in this situation, we're given the second derivative. So here's our second derivative. And we want to find the value of the function, or we want to find the function for the given initial conditions. So we're going to go ahead and integrate the second derivative with respect to t, and that's going to give us the first derivative. And so when I go ahead and integrate this, minus 4 cosine of t, so integrating cosine of t is going to give us sine of t, and so we have minus 4 sine t j, and then we also have a constant of integration here. So let me kind of get that in. Plus, we'll call that C1. So there's our J component. We have a integrating sine. Well, really minus sine, but integrating sine gives us minus cosine, and then times a minus, this ends up being plus 3 cosine t plus another constant of integration in the k direction. And so it also gives us, and you know, when we integrate, I kind of glossed over this, but really let me kind of see if I can move all this over. I can. Okay, really when I integrated, what I didn't say, and let me kind of squeeze it in here, and we have a j component and a k component, but before the j component we really have a 0I component. And so if we're going to integrate that, we're going to possibly at least get a constant of integration. So really we might have out here I'll call it a C3I. We don't know until we look at the initial conditions here. So our initial condition is at time t equals 0, we have a k component of 4. And so if we look at those at the initial condition here, that initial condition is for t equal to 0. Then we have C3I plus negative 4 sine of 0 plus C1j, so I plugged in the t value of 0, plus 3 cosine 0 plus C2k equals 0I plus 0j plus 4k. That's the initial condition. And so now we have to figure out what our constants needs to be in order to make 0I, 0j, and 4k. So to make a 0I, our C3 has to be 0. So I could have left this out completely because I didn't have an initial condition that had an I component anyway. But it's always good to include that just in case. Okay, so for this one, this has got to equal 0. So we need a minus 4 times sine of 0. Well, sine of 0 is 0. Plus C1 equals 0. So C1 also has to equal 0. And then this has got to equal 4. So I have a 3 cosine of 0. Cosine of 0 is 1. So 3 times 1 plus C2 equals 4. And so we're talking about 3 plus constant 2 equals 4, so constant 2 is going to have to be 1, right? 3 plus 1 is 4. So there are my constants of integration. So my first derivative then looks like 0I. I'm going to kind of keep it there because I'm going to integrate it again. Who knows, I might get something. C1 is 0, so it's minus, if C1 is 0, then it's minus 4 sine tj. So minus 4 sine t j. And if C2 is 1, then it's 3 cosine t plus 1k. So plus 3 cosine t plus 1k. So there's our first derivative. Now I also, but I want to find the actual function, so I have to integrate this as one more time. So I'm going to go ahead and integrate this. So in order to find the function itself, r of t, I'm going to go ahead and integrate this. So that's why I kind of kept the 0i there, because I might have a constant of integration pop up here. I don't know. Looking at this, seeing no I component, I'm going to say I don't have an initial condition for the I component, but I'm going to bring it along for the ride anyway, just to verify it. 4 sine tj plus 3 cosine t plus 1k dt. So when I integrate that, let's see, I already used C1, C2, C3. I could start over with C1, C2, C3 if I wanted to. I think I might go on to C4, C5, C6 though, to avoid confusion. So integrating this, there's a potential to get a C4i. Integrating the j component, so integrating sine t gets us opposite cosine, and so so if we have opposite a negative cosine, then we have cosine t, for cosine t, so that's plus 4 cosine t plus a possible c5 for the j component. And then integrating this, if we integrate cosine, we get sine. And so integrating this then is going to get us 3 sine t plus t. Integrating 1 is t. So plus 3 sine t plus t k. And what did I forget there? I forgot my constant of integration. So plus t plus a possible c6 k. So there is my vector valued function. It's getting a little complicated, but let's look at those initial conditions again. So these initial conditions are set up for t equal to 0. And when t equals 0, I have a minus 4j component. That's all I have. So for t equals to 0, I have all of this. I'm going to have c4i plus 4 cosine t plus c5j plus 3 sine t plus t plus c6 k, and that whole thing has to equal 0i minus 4j plus 0k. Okay, so when I plug in a t equal to 0, so so what does that give us? Well, that gives us a C4. There's no t to plug a 0 in for, so just C4 equals 0. So again, I didn't have to include this, but just in case an initial condition pops up for that component, it's always nice to have it there. My j, I have a 4 times cosine of 0. So cosine of 0 is 1. Plus c5, so there is the j component evaluated at t equals 0, and that equals negative 4. So that's 4 plus c5 equals negative 4. Bring this over to the other side, c5 must be negative 8. And then evaluating this at t equals 0, sine of 0 is 0, so we have 3 times 0 T is also 0, so plus 0 plus C6. And all that's got to add up to is 0 for initial conditions. So this is all 0, so that is saying C6 equals 0. So our function then looks like 0i, because we got a constant of 0 here, so 0i. We have a constant of integration of -8, so we have to put that into here. So we have 4 cosine t minus 8. So plus 4 cosine t minus 8 for the j component. C6 is 0. Now this is important though. C6 is 0. The whole thing isn't 0. We're just putting 0 in for C6. So we still have all of this as a result of the previous integration. So we have plus 3 sine t plus 0, but I'm not even going to write that, for the k component. So here's the function. We don't have to write this component, but I'll just leave that there.